So I will be talking about integrability. What is integrability? I was told nobody here knows anything about that, so I will try to talk at a very basic level. But please interrupt me, ask questions. Otherwise, I'm bored by hearing myself talk only. So if you interrupt me, it would be very helpful. So, history recorded John Scott Russell riding along a Union Canal. He saw a certain shape of water, and he followed it riding 20 miles, and it maintained its shape. And he wondered why it was so. In a long passage in his diary. And here is an experiment that reproduces what he saw. As you see, this water shape maintains its form on a long, long distance. Then it will hit a ledge and disperse. It keeps going, going, going. How come it maintains its shape for such a long time? So later on, people wrote down an equation which is called the Korteweg-de Vries equation, written down here. It describes the propagation of water waves in a shallow canal. And what Russell saw was a solitonic solution. Now notice that the solitonic solution evolves in time, maintaining its shape. It does not disperse. If he had the luck to see two solitons, it would also, both of them would evolve without changing the shape. So here is an example again. You see, here are two solitons, they collide. And once they pass each other, the shape is maintained. The same happens for 3 or 4. To appreciate this, let us look at a simple wave equation. Unlike the previous Korteweg equation, here it's a linear equation, while the previous equation was very nonlinear. See, it has phi and product of phi's. So what happens if the equation is linear, a typical wave equation? Then you see, suppose I start with a wave packet, it evolves in time, it broadens out, as you can see here, and disappears. That is what you see in the water fountain. You drop a stone, waves would propagate and disperse, unlike what we saw in the Korteweg-de Vries equation. So why? So there is a beautiful, beautiful mathematical theory behind it. So here's again the equation. And what people have discovered after a lot of effort, that this equation possesses conservation laws. What are conservation laws? These are nonlinear expression expressed in terms of the field phi. So I1 is phi, I2 is phi square, I3 is phi cubed minus derivative square, and so on. There is a mathematical closed expression. So the conserved charge is a local charge, but made out of the derivatives and product of the function, and you can generate them by a recursive formula. What happens then, these conservation laws are maintained in time. Once you have an initial form of phi, evolve them in time, they will still keep their form. So it is an interplay between the linearity, which disperses the wave function, and the nonlinearity, the interaction which keeps it together. And that keeps the form undispersed. So what is classical integrability? In general, a classical system would be called classically integrable if it has n degrees of freedom and also n functionally independent integrals of motion which are in involution. So that means here these are Poisson brackets. They commute with each other, and typically one of these conservation laws, typically I2 would be the Hamiltonian, commuting then with all these currents commute with the Hamiltonian and are preserved in time. And as a result, whatever shape you start with, it will propagate and not disperse. So typically, if you have an integrable system, then the degrees of freedom, let's say QIT and PIT, in terms of which the system is expressed, can be expressed in closed form, and one can really calculate the time evolution of the system for all time, starting from initial conditions, something which typically cannot be done. So a famous example would be a two-body Hamiltonian with a central potential. So Hamiltonian here has 6 degrees of freedom. So governed by a Hamiltonian, P1 square over 2m1, P2 square over 2m1, plus a central potential. The potential depends on R1 minus R2 absolute value. So the 6 degrees of freedom are one can construct integrals of motions which are in involution. So the total momentum P is conserved because it's translationally invariant. The energy is conserved because it's time independent, and because the potential depends only on the absolute value of the distance, the angular momentum is conserved. So it looks like we have 7 degrees of freedom, which 7 conservation laws, which is beyond the number of degrees of freedom, but actually we cannot take the angular momentum 3 degrees of freedom because they don't commute. So we typically take LZ and L square, and then we have 6 degrees of freedom, which govern the motion, as Newton has told us, of a system which will evolve around the center of mass. However, if the potential is not only depending on the distance, but has a particular form, namely it depends on one of them, there is an additional conservation law called the Runge length vector, and given here by the momentum cross the angular momentum minus mk over r absolute value, and it keeps now the system not only evolving in the plane, but maintaining a closed ellipse. And as you know, this is what typically governs the evolution of our planet Earth around the sun. So our system around the sun is actually governed by an integrable model, which we can solve. And as you may know, when Einstein developed his theory of general relativity, he showed that gravity will have corrections. So it's not going to be really a 1 over r potential, but rather there will be a power here, a very small power, which will lead to a precession of the perihelion. And it was discovered and actually measured that Mercury will precess, and that verifies Einstein's theory and violates the integrability of the gravitational, of the 1 over r simple gravitation. If you have not had a good course on classical mechanics, for example, following a book by Goldstein, you can skip this, but typically what one does, one takes the original Hamiltonian, rewrites it in action angle variables of Hamilton-Jacobi approach, does the transformation via a generating functional, and obtains the dynamics of the system, which can be done explicitly if you have these conservation laws. If you have not seen that, don't worry. I'm not going to use that. I want now to go to the main subject that I'm interested in, which is quantum integrability. So quantum integrability, the starting point is slightly different. Okay, so we start with the conservation laws. We have, again, an infinite number of local conservation laws, and I will show now that existence of this conservation law has major implications. One of them is that there is no production. Namely, if you scatter the number of any number of particles in, the same number of particles will come out with the same momentum. That is, of course, if you know about what's happening in LHC, you scatter two particles at very high energy and millions and billions of particles come out because the theory is not integrable. But if the theory is integrable, then we have no production and the momenta are individually conserved. P1 prime and P1 will be equal, P2 prime equal, P3 and P3 prime equal. You can take this three-body scattering problem in and out and arrange it as having only proceed through two particle scattering at a time. So instead of thinking about three particles, first I will have a particle 1 and particle 2 colliding, particle 1, then particle 3, and then particle 2 and 3. Now, typically, this would not be possible because you can say, I can take this 3 into 3 and rearrange them in different order in time. So that first particle, you see, I have exactly the same momentum here and here. Here I'll have particle 2 and 3 scattering first, then particle 1 and 3 scattering, and then particle 1 and 2. Why would that be equal? Typically, it is not equal. However, I will argue that if we have these conservation laws, then we can factorize the scattering of 3 particles into 3 in a consistent way into a series of scattering of 2 particles into 2. Namely, I will argue that the S-matrices of the scattering, namely the S of the two-body problem, namely S2, will satisfy this kind of very non-trivial braiding relation called the Yang-Baxter equation. So you see, you have the S scattering of 2, P2, P3, then scattering of P1, P3, and then scattering P1, P2 to be equal to scatterings in different orders. Namely, the S matrices have to satisfy this non-trivial braiding relation. Braiding because you can think about it as braiding of wires in different orderings. So what I want to do first is to prove that indeed the conservation laws imply these two results, the no production and the factorization. Any questions so far? I always suspect that if there are no questions, either I did such a good job that everybody understands or nobody understands anything. But
I understand.
Okay, good. All right. So let's see. Suppose then I have a scattering state, particles P1, P2 up to Pn coming in. Now, what happens if I have this conservation law? I act with the conserved charge. That's let's say, order 3 on this. And notice that since this is a local charge, local density, it will sample each of them separately, and therefore its action on the scattering state will be that it gives me this expression on each particle's contribution separately, namely separately from here, from here, from here. And the same will happen in the outgoing scattering state. Therefore, what we have is this kind of non-linear relationship between these two scattering states, in and out, which necessarily forces n to the number n of in to be to the number m of out, and the momenta are individually conserved. It should be not k, but it should be p prime I. So that indeed implies a non-production. Now, let me show how Yang-Baxter relationship occurs. So what happens if I act with the nth order conservation law on a scattering state P? E to the IC to this power n will act and pull out this eigenvalue exponential ICP to the power n. So suppose then I have some wave packet. Psi of x expressed here as a Gaussian. And I want to ask, in this Gaussian, where is the particle located? Of course, I can do this Gaussian integral, but suppose I wasn't smart enough to do it, I would do then a stationary phase approximation. Namely, I would take this phase, I'll take its derivative, and namely the derivative of the phase, so it will be ddp of p x minus x0, and put it at the value where this is maximized. So the phase, setting it to 0, tells me that the wave function is located mainly around x equals to x naught. Let us now act on this state, on the Gaussian, with this charge n. So EIC to the IN pulls out now a term EIC p to the n. And now I really don't know how to do this integral, but I can still use the trick. I take the derivative of the phase, which is now given by a p x minus x naught times plus cp to the n, and I discover that the wave packet is located not at x naught, but at x naught minus n cp naught n minus 1. So all I did is take the derivative of the phase and set p to p naught, which is where it's maximized, and I find the location now is shifted from the original value x naught to x naught minus n cp naught n minus 1. If n was 1, this is just a translation operator, right? E to the IP is translation operator. So for n equals to 1, you see indeed that I'm shifted from x to x naught minus c. That is for n equals to 1. But for higher conservation laws, I'm shifted by an amount that depends on p naught. This is a very remarkable result, because that means that by acting with this higher order conservation law, I can take this diagram and shift it. Acting on it, I get a diagram where the order is different. If I had only momentum conservation, then I would shift it all together, but the order of scattering would not change. But because I have this conservation laws, this higher order conservation law, the order changes. And since this is a symmetry operation, I find that the scattering matrices satisfy this relationship, this Yang-Baxter relationship, which guarantees integrability. So that's how the conservation law are responsible for integrability. So let us look at typical models and see how it works. So the most famous example is the Heisenberg chain, or qubit chain in modern parlance, or called the XXZ model. So we have spins arranged in a circle, let's say. We can also talk about in open line, but let's make it simple and impose periodic boundary condition. Then a typical wave function will tell us where the spins are arranged. Let's say site 1 it's up, site 2 it's up, site 3 it's down, and so on and so forth. So the AJs, they tell us what the spin orientation is. And the system is governed by the Heisenberg Hamiltonian, sigma XX, nearest neighbor, sigma YY, plus sigma ZZ, and I can add an anisotropy parameter. When delta is 1, the system is SU2 invariant. And the sigma operators here are just the spin operators, Pauli matrices. So this model was first solved by, in 1931, remarkably very early. Quantum mechanics was discovered in 1925, and the first many-body interacting system was solved already in 1931 by a young postdoc called Hans Bethe. What did it do? He said, let us think about the wave function and think about one particle, namely one spin flip, two spin flip, and so on and forth. So let's start with a ground state where everybody is up, and then flip one spin down, let's say at a position X, and do a linear combination of these. You plug it into the Hamiltonian, and you see that if the wave function is given by an exponential EIKX, this is an eigenstate. That's very straightforward. But what happens if you have two of them? Then they can collide and scatter, and that becomes more interesting. So he took a wave function and he said particle, what happens if particle 1 is to the left of particle 2 with amplitude A12, and particle 2 to the left of particle 1, amplitude A21, again plane waves. So now these are product of single particle solutions, and he showed that if you take this amplitude, plug it into the Hamiltonian, it will be an eigenstate if the scattering amplitude, which gives the relation between amplitude A12 to the left and A21 to the right, if the S matrix scattering particle 1 and 2, namely the relation between the amplitude, satisfies this relationship, then it's an eigenstate of the Hamiltonian. So he solved the two-particle problem. And then what he realized, that he can solve the scattering problem of any number of particles, namely this S matrix, which I can write it as follows. I can write the wave function as follows. It's product of plane wave on the positions of the spin, of the flipped spin, namely position xj is where the spin is flipped down. So I have m flipped down, n minus m up, and the amplitude for each wave function like that relate to the other is given by an S matrix. And so there are m factorial orderings, and we have to ask whether they are consistent. And turns out the consistency relation already shows up when we have three particles. If we have three particles, then we have three factorial orderings, 6 orderings. I can have particle 1 to the left of 2 to the left of 3, particle 2 to the left of 1 to the left of 3, and so on. So I have 3 factorial orderings. So I have 6 amplitudes which are related by S-matrix. So let me start with an amplitude where particle 1 is to the left of particle 2, to the left of particle 3. I exchange particle 1 and 2 that costs me S-matrix 1, 2, and now I have the ordering 2 to the left of 1 to the left of 3. Then I exchange 1 and 3 that costs me S-matrix 1, 3. Now I have the amplitude describing the situation where particle 2 is to the left of 3 to the left of 1. And then I can exchange 2 and 3, and I reach the amplitude where 3 is to the left of 2 and to the left of 1. But I can reach it by a different set of permutation. First, I permute 2 and 3, then 1 and 2, then 1, and then 1 and 3, then 1 and 2, and I can reach the same amplitude. To be consistent, this construction requires that if I choose this path or this path, I get the same wave function. Namely, that the S-matrix must satisfy this Yang-Baxter relation. You look at what I got here, this S-matrix that I computed earlier, and indeed it satisfies the Yang-Baxter relation for 3 particles. And then you can show that if it satisfies it for 3 particles, it satisfies it for any number of particles. So the Hamiltonian then can be solved exactly for any number of particles n with m spin down and n minus m spin up, and we have consistent solution. So that was what Bethe solved, and here you have Yang and Baxter, who first wrote down this consistency condition in a different context. Okay, so now that we have a consistent wave function described being a consistent eigenfunction, we can impose periodic boundary conditions. So we take this chain and identify this state with this state, we get a closed ring, and that means that if I want to take a particle here, take it all the way around and bring it back, I have to get the same wave function. In other words, I start from here, I have to take a product of S matrix, bring it here, another S matrix, bring it here. So I get a product of S matrices, bringing it back. And all I have then is I picked up a phase EIKJL because I moved the particle a distance L around. So I find that the momenta Kj that are allowed satisfy this Bethe Ansatz equation, namely EIKJL must be product of the S matrices that allow me to move the particle from point all the way around. So you see, I obtain here a Bethe Ansatz equation for the allowed momenta Kj, very non-trivial, non-linear Bethe equation that determines the momenta. So I have M coupled nonlinear equation for each Kj, and any valid solution is going to give me an eigenstate with the periodic boundary condition. And once I solve this Bethe Ansatz equation, I obtain the momenta K1 to Km, and from then I can calculate the energy and get the spectrum, all possible eigenstates and eigenvalues. And indeed, this is not a mathematical exercise. There are several materials that people can synthesize, which are described by this one-dimensional model, for example, K copper F3, and people can measure the spectrum of this linear chain. And here is the Bethe Ansatz solution. It's the experimental result, which one can obtain by scattering energy. So one calculates the 6 degree. It's not exactly 0, but it's a good, sufficiently low temperature, and the agreement is fantastic. So a purely mathematical game can describe a real physical system.
Does this only work for like
Sorry?
nearest neighbor models? Like,
That's the nearest neighbor model.
not like if it's like even quasi-local, this sort of technique doesn't.
I'm sorry, Ken.
If it's long-range interacting or like quasi-local.
There are models which are long range and can be solved also. This model is nearest neighbor. Now, not every model can be solved, but there are models which are long range and they can also be solved exactly. So I showed the spectrum. There are more sophisticated measurement. One can calculate thermodynamic plots, and one can compute, for example, the specific heat of the chain. One can calculate the magnetic susceptibility. One can get expression, and again, the computation that from the Bethe Ansatz equation compared to the experimental result is remarkably accurate. So I started by talking about conservation laws. When I solved the model a la Bethe, by Bethe Ansatz, I did not talk about conservation laws, but actually they are present in the background. So I'm going to start now with a different approach, and I will show that there are conservation laws, and they are those that are responsible for the ability to solve the model, for the integrability and consistency. Now, the starting point is beautiful, but not very intuitive, but bear with me. This is a method called quantum inverse scattering. One starts with a 4x4 R matrix, which is solution of the Yang-Baxter equation, which I've written down before. So I write now not S-matrix, but I call it R, just to be consistent with the literature. So R12 U minus V, R13, R23 must be product of these R matrices, product in different order. Notice these are matrices, 4x4 matrices. So this relationship is very non-trivial. Here it's described diagrammatically. So if I find a solution of this form that gives me this answer, then I'll explain now how one uses it to solve the model and how one generates the conservation laws. So indeed, there is a beautiful solution for the R matrix, which satisfies this nonlinear equation. It's given by this expression, sinh hyperbolic lambda plus I gamma, sinh hyperbolic, and so on and so forth, where gamma is related to the anisotropy. If the model is isotropic, then gamma is 0. I will show now that any solution of this Yang-Baxter gives me this commuting charges, and the Hamiltonian in particular is one of them.
Sorry, can I ask, like, how is R related to the model?
2 minutes.
Okay.
Good. So this is a mathematical. So I started with R, and now I will introduce another auxiliary space. That's mathematical magic, where I have the physical amplitudes A and A par, namely describing up and down, are here, and the R, U, and V are in an additional space, which I'll call an auxiliary space. I will take this product of these R matrices. I'll create what is called monodromy matrix, taking the product of these R matrices, take the trace over the auxiliary space only. Diagrammatically, I get this. And I claim that the Yang-Baxter equation that I wrote down for this R matrix makes this monodromy matrix commute with each other at different values of this parameter lambda. I know it's not easy to digest, it's a bit abstract, but my claim now is the following. Once one has this monodromy matrix and expands in the power of lambda, we get these conservation laws, which I declared earlier that they are present. So this conservation law, In to the power lambda n, generate I1, the first conservation, which is the original Hamiltonian. This answers your question. I2, which is a higher conservation law, I3, which is still higher. We have an infinite number of conservation laws. And in particular, the Hamiltonian, namely I1H, is obtained by taking the logarithmic derivative of this transfer matrix. And we have an infinite number of conservation law, and they were in the background and allowed the solution that Bethe obtained. So this closes the circle. I have a model. It has infinite number of conservation laws. They allow me to write down a closed form for eigenstates and solve for them explicitly. So having integrable models, it looks like a very abstract and rare creature. Actually, they appear in any branch of physics: classical mechanics, classical field theory, relativistic and non-relativistic, classical statistical mechanics, quantum field theories in the continuum on the lattice, classical quantum optics, in condensed matter in particular, statistical mechanics, quantum computation, and perhaps also in string theory, because string theory, if you remember, is based on two-dimensional surfaces which are governed again by integrable models. So let me now show how it shows up in a physical system, an experimental system, a Kondo model, which describes experimental data. People started looking at observation, discovered something weird is going on, and it took several decades, and turned out that the system is described by an integrable model called the Kondo model. So it was observed already in 1936 that something strange happens when one measures the resistivity of a metal. It was observed, there are better curves, of course, done later, that when one measures the resistivity and lowers the temperature, the resistivity goes down. That is very easy to understand. The resistivity is due to phonons, that you lower the temperature, you have fewer phonons, then there is less scattering. But then at low temperature, they suddenly so that there is a rise and the resistivity is increasing. Couldn't understand why. And this was not an isolated situation. For example, if you have iron in copper, you'll see this. If you have iron, less iron in copper, you still have it, and so on and so forth. So this is a very stable effect. So, and people were really puzzled. So again, what one looks here at the resistivity as a function of temperature, this is the experimental curve. One understands the black curve, which is due to the phonon. It goes like T to the 3 or T to the 5, depending on the phonon spectrum. But it disappears, the phonon contribution at 0 temperature disappears. And what is left behind is this blue contribution, which increases with temperature. That was very weird because people were used to things going away when the temperature goes to zero. This increased instead. So it took a long time, but it was discovered that this rise here is due to some scatterers, some dirt in the material, to the iron. So what I described earlier, here, to this iron, for example, iron atoms in copper. When the amount of iron impurities was decreased, the effect decreased. So people understood that it's due to this iron impurities. And Kondo wrote down a theory that showed that indeed iron or whatever impurities there are, this could be due to iron impurities or uranium impurities or cerium impurities. They have to have spin in the ground state. So these materials are such that while the outer shell electrons disperse and become the Fermi sea of the material, this inner shell, 3D or 5F, they are still localized and they have net spin in them. And the electrons of the Fermi sea scatter over this spin of the impurity. So what Kondo did is a perturbative calculation of what would be the effect of the scattering of the electrons of the impurity. And he showed that indeed the scattering would increase, very surprising at the time, increase as a function of as the temperature is lowered. Now we are used to things that happen at lower and lower energy and become stronger. For example, QCD, if you know, scattering of quarks increases at low temperature, while if you go or low energies, while if you go to higher energy, it becomes weaker and weaker. But the first example, and this is called asymptotic freedom, and my advisor got a Nobel Prize for it. But actually, Kondo discovered asymptotic freedom earlier, or experimentally, it was discovered earlier, asymptotic freedom. You see, it's called asymptotic freedom because asymptotically, when you go to high temperature or high energy, the effect goes to zero, while if you go to the low energy part, it becomes very strong. In QCD, as you know, at low temperature, I cannot dissociate quarks. The interaction between quarks at low temperature becomes very strong, and that is what is called confinement. So here you have the same effect in this solid state system discovered originally by experiment. So let me show it in the context of a very precisely measured quantity called magnetic susceptibility. So magnetic susceptibility, I have the localized spin, and I'm asking how the spin, the impurity spin, responds to a magnetic field. So here is the impurity, here is the magnetic spin. If I have no interaction, then the calculation of the susceptibility is trivial. I can calculate the magnetization mu up times the probability to be up minus mu down, probability to be down. This is the magnetization at finite temperature of a free magnetic moment. And if you, so that is mu times tangent hyperbolic, if you see this function. I take the derivative, I get the susceptibility, and I see that mu square over T is the susceptibility of just a spin which can be up or down in a magnetic field. You see that it diverges when T goes to 0. Why does it diverge? It's very easy to understand. Spin up and spin down, the difference is delta S is equal to 1. And when you divide it by the magnetization, by the magnetic field that goes to 0, it diverges. So this divergence at T equals to 0 is due to the existence of a net spin in the system. But you do the calculation and you calculate what happens if this spin now interacts with the gas of electrons around it. And you see something very interesting. Instead of the susceptibility diverging at 0 temperature, it goes to a finite value. So notice, at high temperature, the interacting system converges to the free system. This is what I called before asymptotic freedom. But at low temperature, the interaction between the impurity and the electrons becomes so strong that the impurity is screened, and therefore the susceptibility is finite, unlike a free magnetic moment, which susceptibility would diverge. So at high temperature, the free spin susceptibility you see these two lines converge. The interacting susceptibility tends to the free susceptibility, but at low temperature, the spin is screened. That is strong coupling, the analog of in QCD to confinement. So this was an experimental description. Here is the Hamiltonian. Here is the metal. That's a Fermi C of 3 electrons with energy dispersion epsilon k. And this gas of electron interacts with the localized impurity. So here is the term spin density of the electrons coupled to the local magnetic moment. And the coupling constant is antiferromagnetic. So this is a 3-dimensional model. And I can turn it into a 1-dimensional model in a very natural way. Notice that I have an impurity geometry. So I can think about the angular modes of the electron coming in, scattering, and going out. So I take the radial mode or the S wave component, and I obtain a 1-dimensional Kondo Hamiltonian. So this is the kinetic term. This is the interaction with the localized magnetic moment. One computes, again, what happens when an electron crosses the impurity and obtains this S matrix. So that is the J's electron crossing the impurity. You compute this S matrix and the electron S matrix, and you see that they satisfy Yang-Baxter equation, and this allows you an exact solution. So from the Hamiltonian, again, I obtain the S matrices, I examine their algebra, I find that they satisfy Yang-Baxter, and then I can do all the calculations you want, not all calculations. I can do a lot of calculations. So I can calculate, again, what is the magnetization. Here is already the susceptibility I've discussed before. Here is the magnetization. You see, at high magnetic field, that's weak coupling, it tends to the value mu. But if I go to very low temperature, then I go to strong coupling, and it is screened. The susceptibility is finite. You can calculate the impurity-specific heat, and you can calculate for other system too. But notice that here is the specific heat of the model for a impurity of spin half, and this is fit to experiment. So when I'm saying fitting to the experiment, there is one parameter to fit, find what is the Kondo scale. Once you fit that, everything else falls in place. And this is 30 years of data before the model was solved, and it falls precisely on the predicted curve, which you obtain from the Bethe Ansatz. So this is an example of an explicit physical model that you can solve. And that shows that integrability is not just a mathematical toy, as people have believed, but rather describes a physical system. So integrable models in general can describe 1 + 1 system in many areas of physics and mathematics. They allow a deeper understanding and the effects of interaction on all scale of energies. So there is no approximation, say, this is valid at low energy, but not at high energy. They give a full description, and they allow new phenomena to be discovered. But there are many open questions. The methods that I told you about allow you to describe the spectrum. Once you have the spectrum, we can calculate the thermodynamics and so on and so forth. But we still don't know how to calculate correlation function of this model. Major open problem. How to calculate how the system evolves in time. That's still not understood. And the most exciting question is, can one generalize integrability to higher dimension? What would be the concept required in this case? So all the young people here have a list of problems to solve, and let me finish here. Thank you very much.